All right, so what we've established so far is that a piece of solid, round tube steel can be expanded into a hollow piece of tubular steel. And that when we expand it out into a hollow piece of tubular steel, the diameter is increased. But the weight is not increased because it's the same amount of metal. And the actual rigidity of this structure to being deformed by a gravity or weight pressure on this steel, this expanded version of that same amount of steel has an enhanced rigidity against compressive stress or bending stress, because we have in essence taken the metal of the interior portion of this rod and converted it into little struts or trusses that are infinitely wide. But for the same weight of metal, we have enhanced rigidity against deformation stress, or enhanced rigidity as a bridge element compared to this the final point that we want to make is that you can take tubular steel rigid elements and add additional tubular steel rigid elements. And then you can run basically the equivalent of truss bars between the rigid elements. And you can add rigidity to these three tubular steel structures can have additional rigidity added to them by putting supporting structures, essentially trusses, in between them. And as you can see just from watching this is not easy to draw. But the bottom line of it is, if you looked at it from the end, you would have your three tubular steel hollow tube structures, and going in between them you would have truss elements that are rigidifying this combination of these three tubes. And this complete structure has the same rigidity as though you had a solid steel structure of this size, even though this complete structure does not have as much steel in it as a solid steel structure of this size. And this truss-based combination of three tubular elements, this truss-based combination of three tubular elements has more rigidity to it than if you just had the three tubular elements by themselves. Now, A significant design problem with this form of construction is that you wind up with these structures with the tubular elements in them, and they have the trusses that connect the tubular elements together. And when you get an even further distant look at these structures, when you get an even further away perspective on these structures, what you see is this lattice work of support elements going in and out of your main structural beams. And it, from a completely visual point of view, it seems a little busy. It seems industrial, and it's not that pretty. Now, in the old days, this structure could not be bent. So if you wanted to have a bridge deck supported by a truss-based tubular steel structure, you would have had to have made your tubular steel structure in this type of a configuration with these cross members visible, and then you would link up these tubular steel structures. And of course, we're drawing these today as 3. In other words, our tubular steel construction form for these truss-based tubular elements is 3, with the cross links going between the 3 of them. So they would build this. They would have the big joint up here to hold it together, and then you would begin to have support elements that connected the supported part of the bridge to the truss elements. That's what the connection structures are, and this is how they built the bridge with these, because they couldn't bend them. With the advent of inductive heating, which relies on taking an electrical current and putting it through a coil of wire. When you put an electric current through a coil of wire, the effect of this current is that a magnetic field of extreme power is created inside the coil. And if you then take a piece of steel and place this piece of steel inside this coil, then this piece of steel perceives the magnetic field where it's present, remembering that the magnetic field only exists from where the coil starts to where the coil ends. So in this portion of this steel, from here to here, this magnetic field generates heat. And what will happen is that this piece of steel will begin to glow and can get as hot as you want it to get. And it gets hot only in the place where the coil is. So if you looked at it from this kind of a viewpoint, and you had your piece of steel in there, then when you turn the power on, your piece of steel is only going to get red hot in here. That's the only place where it gets hot, because that's the only place where the coil is. And so if you take and place a net bending force on this piece of steel, this is rigid because it's cool, this is soft because it's red hot, and your piece of steel will bring itself into this shape. Because it bends at the place where it's red hot. And this is called inductive heating, inductive shaping, this is the red hot area. And so it only bends here. We're trying to draw this so that from here to here and from here to here is straight. And this bends. And the next thing that they do is they'll take their inductive heating coil and they'll take the piece of steel and they'll put it in here. And they'll make a bend in this area. Then they move the steel, so you're now in this configuration. And your piece of steel has a bend in it now, because that's where they put the heat to it. And then they put this portion of it in there. And they heat this up. And so what they can do is you can take a piece of steel of whatever length you want, and you can apply your red hot heat to this and generate whatever bend you want, and then you can apply your red hot heat to this and generate whatever bend you want there, and apply your red hot heat to here and apply whatever bend you want. And the effect of all of this is that basically they got permission, or they got the capacity, or they got the capability to take pieces of steel and bend them into whatever shape you want to bend them into. And this lends itself to a math analysis. If this happened to be a piece of tubular steel, the math people can give you analysis of how much weight this can support. So if you wanted this to be holding up a bridge element or a bridge deck, then this piece of steel can hold up that bridge deck. And these bridges exist in the zone of this size to the zone of this size. There's a little human being. And this steel goes from 4 to 6 inches up to 10 to 12 inches to 2 feet. And they took the